Hello there and welcome back to this video series on control systems. We have seen that transfer function is the ratio of Laplace transform of output to that of input with all zero initial conditions. And we have seen that TF is defined for linear time invariant systems, and systems that have the same transfer function are called analogous systems. After watching this video, you will be able to specify the transfer function of a general nth order LTI system and also specify what we mean by a pole and a zero. It is essential that we have thorough knowledge of Laplace transforms, of derivatives, integrals, and initial conditions from this point onwards. It would be very helpful if you watch video number 009 in this series thoroughly before going into this discussion and going forward in this video series. With that, we'll jump into the discussion. Consider an nth order LTI system described by the differential equation given here in equation 1. This a sub n minus 1, a subscript 1, and a0, all these terms with b subscript m all the way up to b0, these are constant coefficients. An nth order system, nth order linear time invariant system, is described by a differential equation with constant coefficients where you have nth derivative appearing. In this equation, x of t is the input signal given to the system. Y of t is the output coming from the system. With these two defined and also the definition of Laplace transform of the input signal and the Laplace transform of the output signal. Input signal is lowercase x of t and its transform is uppercase x. Output signal is y of t, lowercase y, and its Laplace transform is uppercase y of s. And all these are initial conditions, that is y evaluated at time t is equal to 0, first derivative of y evaluated at time t is equal to 0, second derivative of y evaluated at time t is equal to 0. Similarly, all the other x derivatives. This dash here is called prime and it indicates one derivative. If you have one prime, it is first derivative, second derivative. Similarly, derivative, nth derivative, here it is mth derivative. All the initial conditions are 0. With these definitions and 0 initial conditions, we can see that Laplace transform of derivative of y is sys. Of course, we have minus f of 0. But all the initial conditions being 0, it comes out to be sys. Similarly, the Laplace transform of second derivative of y is s square and so on. So with 0 initial conditions, you can see that differentiation in time domain is simply multiplication with s in Laplace domain. With this, you can write equation 1 as given here. It's an algebraic equation. Okay. A n s to the power of n ys, a n minus 1 s power n minus 1 ys, and so on. Similarly, the same with x. Thus, in Laplace transform domain, the differential equation comes out to be this, and we can write the transfer function as indicated over here. This ns is the numerator polynomial in s. This ds is the denominator polynomial in s, and we have transfer function as ns over ds. If you equate the numerator polynomial to 0, you get what are called the zeros of the transfer function. That is, this m order ns equal to 0 will give you the zeros, and this numerator equated to 0 will give you what are called poles. There are m number of zeros, n number of poles. For all real life LTI systems, this n is greater than or equal to m, and in such case it is called proper transfer function. So to summarize, we'll once again state that TF is the ratio of Laplace transform of output to that of input with all initial 0 conditions. The m roots of numerator polynomial are called zeros, and the n roots of denominator polynomial are called poles. N is greater than or equal to m for all practical systems, and in such case the TF is called proper TF. That's all we have for now. Have a great day.